Here we have section 3.1, which is talking about numeration systems. Now, in this section, we're going to talk about some different numbers around the world in history, um, very briefly, but we're going to really concentrate on different base systems because it's one of those things that if you really understand how the numbers work, then you'll be able to teach it better to young children. So we want to make sure that you understand how our number system works inside and out and why you're doing what you're doing that will help you be a better teacher. Okay, so we use a base 10 number system, and that's probably because we were born with 10 fingers and toes. So it was easy counting. The Latin word for fingers and toes is digitus, and guess what we call the numbers we use? Digits. So it comes from the Latin word. I think that's pretty interesting. Now, because we have a base 10 system, we use the digits 0 through 9 to represent the concepts of the numbers. I mean, these symbols that we use, we have a hard time distinguishing them from being the numbers themselves, but they're just what we use to represent those numbers. And in civilizations past, they used different things, pictures and letters and different things to represent numbers. So this is what we've grown up and become accustomed to, but it wasn't always that way. Now, the written representation of these numbers is what we call numerals. So the word numerals literally is the written representation of a number. Now, different cultures throughout history have used different symbols to represent their numbers. So here is a little chart that has some very interesting um, pictures of the different things that have been used over the years. And we use what's called the Hindu Arabic system. The numbers, the numerals rather, written out 0 through infinity. But this is technically called the Hindu Arabic system because it was originally invented um, in India, and then it was brought over by the Arabs whenever they came into Europe, and then of course then it traveled on from there. So that's our current system. But now over the years, I want you to look at some of the different things that they did. In Babylonian culture, they use these little kind of like triangle looking things that represented the numbers. And when they got to 5, they started stacking them. And then whenever they got to 10, they started using this little weird shape here. Now, I think that's pretty cool. So, and then of course they started pairing them up. So 11 would be one of these symbols with a little triangle behind it. So that's kind of cool. In Egypt, and in just a few minutes I'm going to show you a more detailed picture of Egyptian numbers, but they use these things. This is called staff, and they use that for 1 through 9. Or yeah, they didn't even have a 0. Notice that, and neither did they in Babylonian numbers until they got to the number 10, and then they use this symbol that they call a heel bone. In Mayan culture, notice that the Mayans were actually the first to come up with this concept of a number 0, and then they used a series of dots and lines in order to represent their numbers. Greeks used the lowercase alphabet. Romans used a capital alphabet with, and we'll go into more about the Romans here in a little bit too. Originally, this is where we came from with the Hindu numbers. They had a 0, and if you'll notice, then the numbers start to look a little bit more similar to ours. And then this was the original Arabic. So very interesting. Now, our system is called the Hindu Arabic system, and we've all, I say we all, way back when, they agreed to use the base 10 system, and that required 10 digits because it's a base 10 system. So each digit represents a place value of a power of 10. So say we had this number here, 65,984. The 4 we know is in the ones position, the 8 is in the tens position, the 9 is in the hundreds position, and so on and so forth. But those are all powers of 10. Even this ones position, oops, let me get rid of that and let me write with a pen. Even 10 to the 0 is technically 1. Remember, anything to the 0 power is 1. So we have 10 to the 0 power is our ones position, 10 to the first, which is 10, that's our tens position. 10 squared is 100, so that's what makes our hundreds position, and so on and so forth. Now, this is important to understand because if you truly understand the way our number system works, then you'll have an easier time working in other base systems, and that just reinforces your understanding of our number system. And then when you get to doing things like if for some reason you ever had to teach fractions one day or something, you wouldn't be teaching them just to borrow a 1 and stick it over there because you would have a better understanding of number systems and know that that's not allowed. All right, let's see what else we have here. Each position of a digit in a number represents a value multiplied by a power of 10. That's what we just talked about. So, for instance, the number 65984 is read as 65,984. Now, notice I didn't say 984, which is a big common mistake that I don't want you guys to make. You do not read the word, or the number using the word and. And the word and represents the decimal place. So the only time you would use and is if you were reading something like this, 5.5. You would say 5 and 5/10. So be very careful about that. I hear it all the time, and it is not proper. But we could write this out using the place values because 4 is in the ones position, so that'd be 4. 8 is in the tens position, so that would be 8 tens or 80. 9 is in the hundreds position, so that would be 9 hundreds or 900, and so on and so forth. Now we could also write it out in what's called expanded form using those place values as powers of 10. Because 4 is in the ones position, it would be 4 times 10 to the 0, which is a 1. And then we would have the next position would be 10 to the first, or 10. The next position would be 10 squared, or 100. The next position would be 10 cubed, or 1,000, and so on and so forth. So, really understanding, and not taking for granted what those numbers are is really, really important when you're going to be working with small children and helping them learn. All right, now, here's what I was talking about when I said we were going to talk more about the Egyptians. The Egyptians, they had some really cool and interesting hieroglyphics that they used to represent their numbers. So we have this straight line, which was called a staff, and it's worth 1 of our numbers. Then this little upside down U, which is called a heel bone, which for us is worth 10. And then they had this really cool little curly Q here that they called a scroll, and it's worth 100. So you can see that they actually had kind of a base 10 system. They really did. They just used hieroglyphics to represent the place values. So, for instance, in Egypt, if you had something written like this, the polywog here represents 100,000, so that's here. And then you've got 3 of these scrolls. Well, the scrolls are worth 100, so that's 3 hundreds. And then you've got 2 of these little curly cues, which mean a heel bone, so those are worth 10. So that would be 2 tens or 20. And then you've got 2 of the staffs, which are worth 1, so that would be a 2. And whenever you add all that together, that would be 100,322. All right, now I think we're going to talk about the Babylonians next. The Babylonians had a really interesting number system. And why they did it this way, I don't have any clue. It would be really cool to research that and figure out why. But their number system was actually a base 60 system. But even though it was a base 60 system, they actually only used 2 different symbols. They had this little triangle symbol that was worth 1, and then they had this little, I mean, to me it looks like a less than sign, and that was worth 10. So it just so happens, though, that because it was a base 60 system, each one of their place values would be a power of 60 instead of ours being a power of 10. So if you had a again, let me get rid of that. If you had a 3-digit number, let's say, this first position would be 60 to the 0, or the ones position. Then the second position would be 60 to the first, or worth 60, however many they had, you'd multiply it times 60. And then this third position would be 60 squared. So you would end up multiplying out whatever this was times 3600. So that's very interesting. Now, another very interesting thing that they did is that they used a separation in order to show place value. So here we have the ones position, so that would be 60 to the 0. Then you have the 60's position, or 60 to the first. Then you have the 60 squared position, and then the 60 cubed position. So what this number represents to us would be a 1 times 60 cubed. So that's right here, the 1 times 60 cubed. Here we'd have 10 and 1, or 11 times 60 squared. Here we would have a 10 and a 1, so that would be 11 times 60 to the first, which is 60. And then we have a 1 in the ones position. So if you were to multiply and add all those together, this number that they would have written out represents 256,261. Very interesting system. Not very practical, but I mean, it would be very difficult to work with a base 60 system, so we don't use that, of course. Now, the Mayans also had a very interesting number system, especially because they were the first ones to talk about the concept of 0 being a number and not just meaning necessarily nothing, but being an actual number, an actual concept. So they use this really cool, kind of almost looks like a seashell, or clam shell or something like that, and that represented 0. And then they had these dots that represented 1, and then they had these lines that represented 5. Now, the Mayan system, because it is so complicated, we are really not going to talk about it very much. I just wanted to kind of give you guys a brief introduction into it, because their place values were based on sort of a base 20 system, but they also multiplied that position by 18 once they got past the 20 to the first. So again, if you had a 3-digit number, say, in the Mayan system, this first position would be 20 to the 0, which is a ones position. And the second position would be 20 to the first, but then the third position would be 20 squared times 18. And then each one after that would be 20 to a power times 18. And another thing that they did was they didn't write their numbers out side by side horizontally like we do. They actually wrote their numbers out, and I didn't show you a good example, but there is one in the textbook that would show you that they would list out their numbers, like say if they had a 1 in the ones position, it would be a dot, and then if they had a 5 in the next position, it would be a line. And then let's say they had a 8, they would have a line with 3 dots in the third position. They went vertically up. So that's gets to be very complicated, and especially with that multiplying by 18, it's something that we're just not going to tackle in this class. But something we are going to work on is Roman numerals, because we have those, we see those constantly, so you do need to know what those mean. I mean, at the end of every TV program or movie, they have the date that it was done, out in Roman numerals. On buildings and things like that almost always have Roman numerals that show when it was built or established or whatever. So it's a prevalent part of our culture still. Now, in Roman numerals, the 1 is worth 1, the V is worth 5, the X is worth 10, the L is worth 50, the C is worth 100, the D is worth 500, and the M is worth 1,000. And so they could write any number they wanted to using just those symbols. So to write a number, they never use more than 3 of the same symbols in a row. So if they needed to write a fourth one, they use a subtraction method. So in that case, which I'm sure you guys are familiar with, the number 4 is written as IV, because it's 1 less than 5. So, meaning 1 from 5. So the number 99 would be written IC, meaning 1 from 100. So I put in here a table of examples so that you could see that, and I think that's kind of cool that they did that. So very interesting. Now, I said this brings us to the coolest part of this section, which is learning about other base systems. And I said again, when you really understand our numbers or our base 10 system, then the other base systems are the exact same concept. It's just using a different base rather than 10. So in our base 10 system, we already talked about how each place value is a power of 10. So we needed 10 digits to represent that. If we have a base 2 system, we need 2 digits to represent it. If you had a base 3 system, you'd need 3 digits to represent it, and so on and so forth. So let's talk about how we would convert in a base 10 system. Okay, so before we do that, let's take one more look at our system, and then we're going to use that and apply it to a different base system. So let's say that we have this number 24985, 24,985. Notice I didn't say the word and, because that's not a decimal. We assume that to be a base 10 because it doesn't have anything below it. If you have a different base system, you have to identify it like this. So, we just assume that all numbers are base 10 because that's what we use all the time. But let's look at what that means in reality. Okay, so in our base system or our number system, we start reading them from left to right, but we know that the place value starts at the right and then gets bigger as it moves to the left. So we're going to start with that. This 5 represents 5 times 1, which is 10 to the 0. And then we would add that to 8 is in the tens position, so that would be 8 times 10 to the first, plus, and then this 9 is in the hundreds position, so that would be 9 times 10 squared, plus, then the 4 is in the thousands position, so that would be 4 times 10 cubed, plus, and then we have a 2 in the 10,000th position, which would be 2 times 10 to the fourth. So you see how the place value is multiplied by the number that's in that position. Now we've grown up with this, so we don't even think about what's really happening there. But I want you guys to be more knowledgeable and to be more understanding of the number system so that you can pass that along to your students and help them to understand even more about the number system. So now, if you can wrap your head around this, then other base systems become the exact same concept. So let's say that we have a number 11244 base 5. Now that's the way we read that, but we don't say it's 11,244 because it's not base 10. It's 11244 base 5. So this is a base 5 number because of the subscript. So let's see what it would actually be in our numbers. So taking that same exact concept, we would start with the first position is 4, and that would be 5 to the 0 because it's a base 5 system this time instead of a base 10. So plus, now our next one is going to be multiplied times 5 to the first, and there's a 4 in that position. Plus, the next place value would be 5 squared, so then there's a 2 in that position, plus, and then the next position would be 5 cubed, and there's a 1 in that position, and then the next place value would be 5 to the fourth, and there's a 1 in that position. So each one of these represent the place value, and each one of these represent the number in that place value. Now, if we were going to convert that over to our numbers, we could very easily, because 5 to the fourth is 625. So this would be like saying 1 times 625 plus 1 times 5 cubed is 125 plus 2 times 5 squared is 25 plus 4 times 5 to the first is 5 plus 4 times 5 to the 0 is 1. Okay, so then going back, we can say 1 times 625 is 625, plus 1 times 125 is 125, plus 2 times 25 is 50, plus 4 times 5 is 20, plus 4 times 1 is 4. And if we add all of those together, we get the number 824. So the number 824, I think I said and there and I shouldn't have, 824 is a base 10 representation of the same number 11244 in a base 5 system. Very cool, huh? And if you go backwards and you want to convert a base 10 number into a base, let's say 5 number, then you would just have to go backwards and kind of think in terms of groups. So this can get a little bit tricky, so you may have to really think about this as we go through it. But think about your place values first. So we know that we're going to have, since we're going to go backwards, we're going to take this 824 and go backwards to the base 5 system. So our first place value would be times 5 to the 0, so we have something times 5 to the 0, plus something times 5 to the first, plus something times 5 squared, plus something times 5 cubed plus something times 5 to the fourth. Now, we don't really have to go any bigger than that because our next place value would be 5 to the fifth. And if you do on your calculator real quick, 5 to the fifth is 31 3,125. Well, 3,125 is much bigger than 824. So there's no way we could have groups of that inside 824. And we'll work some more on this. We'll do some examples so you'll see what I'm talking about. All right, so 5 to the fourth is technically 625. So we want to figure out how many groups of 625 are inside that number of 824. So in order to do that, we need to do the division. 824 divided by 625. Well, we know it'd only go in there once. So if I then finished out the division, I would be left with 199. So that means it's going to go in one whole time with 199 left over. Okay, so now we have 199 that we're working with. Our next place value is worth 125. So I need to go ahead and divide this by 125 and see how many of those groups are in 199. So 125 will go into 199 once. And if I finish doing the division, that's going to leave me with 74 left over. So there's one group of 5 cubed with 74 left. Our next place value is worth 25, so I'm going to divide by 25. 25 will go into 74 twice, with 24 left over. So there are two groups of 25 with 24 left over. This next place value is worth 5. So if I divide 24 by 5, it goes in 4 times with 4 left over. So it would go in, there'd be 4 groups of 5 with 4 left over. Our next place value is worth 1. So there would be exactly 4 groups of 1 left over. So that makes our number 1, 1, 2, 4, 4, base 5, which is exactly what we said it should be. Alright, now one last thing before we start actually working some examples. We can use this same exact concept for any base system. If it's a base 3 system, then your place values would be 3 to the 0, 3 to the first, 3 squared, 3 cubed, 3 to the fourth, so on and so forth. And these are real things. Computers are done on what's called a hexadecimal system, which is a base 16 system. And they also work with a base 2 numbers, which just have zeros and ones, and that tells things to turn on and off. This is what this is all built on. So it is something that is used in the world, and it is important to understand. It's not just weird stuff that we have you do to try to trip you up. Now, any of these base systems can be worked with. Where it starts getting tricky is where you have something that's above a base 10 system. And generally, the ones that we have that are above a base 10 system that are used are only a base 12 system, and then, like I said, a base 16 system, which is used in computers, that hexadecimal system. So if we have a base 12 system, we would need 12 digits. Well, you can't have 2-digit numbers. Digits mean single numbers. So in a base 12 system, since we need 12 digits, we run out of digits when we get to 9. So they use T for 10 and E for 11, probably because of the word 10 and 11, the first letters of the word. For a hexadecimal system, a base 16, we would need 16 digits. So we run out, oh, there should be a 0 there. We run out of digits when we get to 9. So then they use A, B, C, D, E, and F for 10, 11, 12, 13, 14, and 15. And then whenever you get to, if you can't use 16 in a base 16 system, that would be one group of 16, which would be another place value. So I hope that that hasn't completely thrown you. Let's work some examples and see how this stuff is all going to work.